Okay, guys, today we're going to do a simple recap on an energy problem. And then what I'll do is we're going to continue with our kinematics chapter, right? So I've mentioned in my last lecture, basically, this problem where you had like semi-dome, right? And we have an object on this dome. And what I would like to do is I would like to find, the velocity of this object at any instant, right? Obviously, this is, and this guy has a mass m, right? And then I'm going to establish this angle theta, right? So how do I find, the velocity of this object at this position, right? Here, I'm going to assume that there is no friction. Mu k is actually equal to 0, so there is no friction. How do we do that? So if you use energy, we can say the energy at state 1 is going to be equal to the energy at state 2, right? And here, obviously, we have to have some initial velocity be 0, and we're trying to find the velocity at this point, right? So E1 is going to be equal to 1 over 2 V0 squared, right? Plus the potential energy. So here, V, so I'm going to call this guy my reference, right? The potential energy is 0, right? So at state 1, I'm going to have mgr, right? And then E2, I'm going to have 1 over 2 m V1 squared plus the elevation, which is mgr cosine theta. So I could use this, and from here, I can find the velocity at state 1, right? So here, if I can actually cancel out the m's, and I can multiply it by 2. So 2, 2. So I'm going to end up with V1 squared is equal to 2gr 1 minus cosine theta plus V0 squared. So I can actually use this guy to find this velocity. So in one of the previous problems which I was solving in the initial lecture, we actually had the coefficient of friction. And turned out that if you actually have friction while this guy is rotating, you would have to have a nonlinear velocity, which is not going to be covered in what we're discussing. So having friction here will actually make this problem nonlinear, and you won't be able to solve it based on the stuff that we have been discussing in this class. But however, things that I could ask you on this problem is, find the angle where the normal force basically, or when this object is about to take off from here, right? So what you would do here, or find the angle where basically where this guy begin to lose contact with the surface. And to do that, basically what you do is you have to do a free body diagram, right? So this is your N, and this is your mg. And obviously you are going to have this mv squared over r, and you basically find where n is going to be equal to 0, right? So if I ask you at what angle the object begin to leave the surface, this is your homework assignment, for example. This is actually one of the homework assignments. So to do that, basically, we want to set up a free body diagram and then find when n is going to be equal to 0. So how do you do that? So you sum the forces along the normal, and you're going to end up n. So if this guy is n and this guy is theta, so n minus mg cosine theta is going to be equal to mv squared over r. And this is going to be my velocity. When n is equal to 0, then mg cosine theta is essentially equal to mv squared over r, right? Or m and m will actually cancel out. So what you do here is you're going to take, so this is your velocity, or this is your V1 velocity. V1 squared over R is equal to G cosine theta. So you take this guy and then you put it here, right? So V1 squared is going to be equal to RG cosine theta is equal to 2GR 1 minus cosine theta plus V0 squared, right? And RG cosine theta is equal to 2GR minus 2GR cosine theta plus V0 squared, so 3GR cosine theta minus 2GR is equal to V0 squared, right? So from here, basically, we need to put these together. So 3 gr cosine theta is equal to v0 square plus 2 gr. So cosine theta is going to be equal to v0 square plus 2 gr divided by 3 gr. So what is the issue here? So if v0 square is greater than 1 gr, then cosine theta will always be greater than 1, right? And in that case, your part will basically never leave the surface, right? So if v0 square is very large, right, then your object will never reach the surface, which makes sense, right? So if v0 square is very large, it means that even at this point, basically, your normal is 0. Okay? Even at this point, if your velocity here is sufficiently large enough, even at this point, basically, you will have, as a result of this mv square over r going downward, then this guy wouldn't be reaching this point. Okay, so this is the type of questions that I might be asking you guys on an exam. Okay, guys, so this is what I did, right? So use the conservation of energy to find the velocity of any point on a sliding on that sphere, right? So this is going to be our velocity, and to find, to relate the energy or to find the forces, you just use summing the forces, right? And here we sum the forces along the normal. We got n minus mg cosine theta. Right, because this is my positive direction, mg cosine theta, right, is going to be equal to minus mv squared over r. So I put this guy, so if n is going to be 0, right, to find the point where the object begin to leave the surface, then mg cosine theta is going to be equal to mv squared over r. I removed m, so v squared over r is equal to g cosine theta. So this relationship have to be equal. So v squared over r, or v squared have to be equal to r g cosine theta for you to leave the surface. So I replaced this velocity squared over here, and I solved for cosine theta, which was equal to v0 squared plus 2gr over 3gr. So I know that cosine theta always has to be less than 1, right? Cosine 0 is 1, cosine 90 is 0, right? So cosine theta is always a number between 0 and 1. If cosine theta is 2 here, then theta is equal to inverse cosine of 2, which is undefined, right? In that case, you will never find the angle theta. Why? Because your velocity is greater than gr. Your initial velocity is greater than gr by summing these three, meaning that even at that instant, basically, your block wouldn't be sitting on it, and would be basically 0 at this point if v0 is equal to gr, because, or I'm sorry, if v0 squared is equal to g. If v0 squared is equal to g. Okay, guys, so this is it regarding this problem, and I'm going to basically continue with kinematics, and
Doctor, I have a question.
yeah, sure.
How we do the friction, the work of a friction on a non-constant,
Like here, for example.
And a various, yes, trajectory, yes.
Okay, so if you were to calculate the work of friction over here, right? Here's what you'll do. Okay, so we've actually tried to work on this problem in the previous session, and it turned out that, once we do this, basically you will not be able to solve for the velocity, right? In that case, because you will be able, but you would have to use like nonlinear integrations. Okay, sorry about that. So let me show you. So this is what you have here, and let's say this is your object, and then, okay, let's say here you were to take into account the work of friction, right?
Yes.
So let's say this is state 1, and then this is state 2. So the friction is going to be obviously always. So this is your normal force. This is your mg, and then this is a friction. Friction is going to be equal to mu k times n in this case, right?
Yes.
let's say if you were to analyze this on any point, then this is going to be your normal. This is going to be your, I'm just going to keep it F. This guy is going to be your mg, right? And this guy going from here upward, this guy is going to be your theta. Okay, does that make sense?
Yes.
So on your acceleration diagram, we know we always have here mv squared over r, and we actually have this mat. Okay, if I sum the forces on the upward direction, I'm going to get what? N minus mg cosine theta is going to be equal to this, right? Minus
Yes.
mv squared over r. So your normal is going to be equal to mg cosine theta minus mv squared over r. So
Here
here,
the n is not 0.
I'm sorry?
The n here is not 0, so here it does not leave the track in that state. I mean.
What I'm saying is I'm just, so this is a different problem. So right now we're solving the same problem, but by adding the friction.
Okay, okay.
Okay, and here this equation simply tells you what is the normal force. The normal force is going to be equal to mg cosine theta minus mv squared over r. Why? Because once you have velocity, basically, you reduce your weight. In this case, you reduce the apparent weight, right? So the normal force basically reduces as a result of the velocity, because once this guy is like, you know, rotating, then you need basically less force to basically apply on. How about what is going to be the friction? Well, I know the friction force will always be equal to mu k times n in the case of a moving object, right? So the friction is going to be mu k mg cosine theta minus mv squared over r. What is the work of friction? So if the object moved from here to here, so the work of friction,
We should integrate.
exactly, you integrate F times ds. So
Yes.
from state 1 to state 2, I know here the friction will always be opposite to ds, and I can convert f ds to r d theta. So this would be F times r d theta from 0 to some value theta. And what is my F? In this case, it's going to be 0 to theta, right? F is going to be mu k times n, right? Which is mg cosine theta minus mv squared over r, right? D theta. So this is your work of friction. So obviously I can integrate the first portion here, but I won't be able to integrate this part. Why? Because the velocity itself is actually variable, right?
Yes.
To do this, you actually have to integrate AT, right? So we need to find AT. How do you find AT? Just sum the forces along AT direction, and you are going to get from here, we have only mg sine theta, okay? So mg, right, sine theta minus F is equal to mat, right? So
Yes.
mg sine theta minus F, which is mu k times n, is equal to mat. So I'm gonna replace this by whatever we have. So mg sine theta minus mu k times n, which is here, mg cosine theta minus mv squared over r is equal to mat. So I'm gonna knock down the m's, and ultimately I'm gonna end up with at is equal to g sine theta minus mu k g cosine theta plus mu k v squared over r. So I need to get the velocity. I still don't have the velocity. So now the acceleration, the tangential acceleration, is actually a function of your velocity squared. So I know at is going to be equal to dv over dt. That's going to be g sine theta minus mu k g cosine theta plus mu k v squared over r. Okay, so we're going to stop right here. Why? Because if you integrate this, you have to actually take this whole thing, put it down, and then you have to integrate dv over this guy, right? Which is a nonlinear solution, right? So we can't solve this in our class. Obviously, you can solve it numerically in Maheke, but solve it here, obviously, I won't be giving you this on the exam. So if anything, I would give you, you know, find the angle where n will basically be 0, right? Just like what I solved earlier. Does it make sense?
Yes. D. Okay. Thank you.
Okay, so this is what we. It looks like you are the only one actually who's attending now. So, okay. So I think next time what I'll do is I'm just gonna do one lecture, you know,
But I won't be able to attend the first one because I have a class.
you won't be able.
No, I have a class at 10.
You have a class at 10. Okay. Okay, I guess we'll discuss it when we come to it. Okay, so hala, what I'll do is I'm gonna solve example 7, and let me share my screen. There you go. Okay, so this is called a planetary gear box, right? And the reason why it's called a planetary, because it looks like the planetary system. You know, the planetary system where we have a sun, right? This component here is called the sun. This guy is called the sun, and this guy is called the planet. Okay, and we know the planets basically orbit around the sun, like, you know, planet Earth basically orbit around the sun, and this is called the planet, and this guy is called the sun, and this guy is called a ring. So these are the 3 components in a planetary gearbox. And in this course, basically, you know, we need to just be able to evaluate the velocities at various points on this planetary gearbox. And this is what I have here is. In this problem, basically, what we have is we have this link, right? This part right here is actually called the arm, all right, or the carrier. And the arm basically tracks the velocities of the center of the planet. We know every point here is going to have different velocity, but this guy basically is tracking the orbit velocity of the planet. So when this guy rotates, basically, this guy is going to be telling you the velocity of the center of the planet. Okay, does it make sense?
Yes.
Okay, very good. All right, so in this problem, they gave us that omega dE, right? Angular velocity of this carrier or arm, right? And we would like to find the angular velocities of this planet and the angular velocity of the sun. So how do we do that? So I think what we can do is, first of all, we can get the velocity of point C, right?
Yes.
We can get the velocity of this point. Do you know how do you get the velocity of this point?
We choose another point that is E, and
Okay.
we do the formula.
Exactly. So let me see if I can actually write it. So I can say omega d, okay, is equal to, or I'm sorry, the velocity, right? So the velocity of d is going to be equal to the velocity of E, okay, point E.
Yes. Plus omega times.
Plus omega cross
RDE.
RD with respect to E. In this case, we know V is going to be 0, right? So we're going to end up with this, right? And if we, you know, for a minute ignore the directions of these, so I'm just going to end up with omega multiplied by the distance, right? The distance between ED. So I'm just going to make it ED, okay?
Yes.
Which is going to be equal to how much? 18 multiplied by distance ED, which is how much? So we know this guy is 0.2, and then this guy is how much? 0.3, right? So 0.2
yeah. Plus 0.3.
Plus 0.3. Okay. Let's see if I can actually move this. Okay, very good. So next step is, now we find the velocity of d, right? Let me actually do this very quickly. Okay, so 18 times 0.5 is how much? 9, right?
Yeah.
So Vd is equal to 9, okay, meter per second. Okay, very good. So next step is we would like to find what? We would like to find the angular velocity of the planet. How do I find the angular velocity of the planet?
We can choose another point on this planet, and we have the VD now, and we applied the same formula.
Exactly, yes. So what we'll do is, okay, what is the other point that we have to choose? Do we know the velocities of any other point on the planet?
We should choose a fixed one to be 0.
Okay, exactly. We should choose a fixed one, right? It doesn't have to be a fixed one. If you know its velocity, then it's fine. You need 2 points. But here, they tell us that this epicyclic gear train consists of the sun gear, which is in mesh with the planet. Okay, the gear has an inner hub C, which is fixed to B, and in mesh with a fixed ring gear. So this planet, right, is in mesh with a fixed ring gear R. Okay, meaning that a point here, right, would actually have what? Zero velocity,
A 0
right?
velocity.
Why?
Yes.
Because the ring is not moving, right? So when that point touches the ring gear, it will always actually have a zero velocity. So maybe we can use this point to actually get that. So here, what we can do is we can say that this VD is actually equal to omega of the planet multiplied by this radius, ما هيك اللي هو radius of the planet, right?
Yes.
By planet radius. Which is equal to how much? Omega of the planet is equal to, we don't know it, right? So planet multiplied by planetary, which is equal to how much? 0 point, so inner planet radius, right? So the top should be inner. Because it has 2, right? Inner. Okay, inner planet radius is equal to 0.1, right? But we know this guy has to be equal to VD, which is equal to how much? 9.
Yes.
So basically, omega of the planet is equal to 9 divided by 0.1, which is equal to 90 radian per second. So now we get the angular velocity of the planet. Next step that we have to do is we need to get the angular velocity of the sun gear. How can I get the angular velocity of the sun gear? So I think I'm gonna need to get the velocity of a point somewhere here, right? So I need to get the velocity of this point, right? Which is not on this carrier, it is below it, behind it, right? And let's call this point G, let's say, right? How do you get the velocity? We can actually get the velocity of point G, which is common to the sun and to this, and we can use the velocity of that point to find the angular velocity of the sun gear. So I can say velocity of point G is equal.
So here we can choose the point E or the point D that we calculated before, right? Because it's a common point for the 2 gears.
Exactly, yes. So I'm calling this point G, right? So omega planet multiplied by the distance. I could easily use point D or this point, right? The point that has 0 velocity, which is easier. So the distance from here to here is equal to how much? Well, let me draw it. Yeah.
Can't we choose E, the point E?
Okay, well, point E doesn't belong to the planet. Okay. Right? Point E doesn't belong to the planet. So we need to get the velocity of this point, right? Of this point, because this point belongs to the planet and also it belongs to the sun, and we can use this point to find the angular velocity of the sun. But we can find this velocity first using the angular velocity of the planet. So velocity of point G is here, like I mentioned. Here.
Yes.
Right? Yeah, this is point G. We can change the color to black maybe. Okay, so this is point G. And velocity of G is equal to omega of the planet multiplied by how much? By this distance, right? This arrow right there.
Yes.
Which is equal to how much?
0.4. 0.4.
0.1 plus 0.3, right?
Yes, 0.4.
Okay. which is equal to 90 multiplied by 0.4, right? What is 90 times 0.4?
36.
36, okay, thank you so much. Okay, so now we need to find the angular velocity of the sun gear. How can I find the angular velocity of the sun gear?
We have the velocity of g and velocity of e, which is a fixed point.
Exactly. Yes, very good. So the velocity of E or G, sorry, is equal to omega of the sun because it also belongs to the sun multiplied by the radius of the sun, right?
Yes.
Sun radius, which is equal to omega of the sun multiplied by the sun radius, which is how much?
0.2.
0.2, and this guy is equal to how much? 36, right? Then omega of the sun is going to be equal to 36 divided by 0.2, right?
Yes, 180.
Thank you so much, 180 radian per second. Okay, I think it's all good from here. Okay, so this is a technique for analyzing the angular velocities of a Planetary Gear Box, and then you can see really it's very straightforward here. Okay, very good. So let me go into next problem and clear all my drawings. Okay. Let us actually work on this problem. Here we have these two sliders, right? This guy is moving with this velocity downward, right? And then this guy would have to is constrained to move horizontally. This guy is also constrained to move horizontally, and then we need to find the velocity of point E. How are we going to be able to do that? Here, what I'll do is I'm going to stop shading, and then I'm going to redraw it over here. Okay, and so this is what we have. So we have okay, and this is point D. Okay, so we need to find the velocity of point E, given that point A is moving downward. So every time you have a kinematics problem, the first thing that you have to do is you have to establish a frame, right? And this is my IJ frame. Do you see this well, right?
Yes, yes.
Okay, very good. And we know VA is equal to 4 meters per second. So one thing, I think this and this, we should be able to get the velocity of point D, right? This is independent, that link is independent. So this and this, they would allow us to find the velocity of point D, and the velocity of point D and the fact that this guy is constrained, we should be able to find the velocity of this guy, all right? And the reason why we can do this is because when I write the vector equation, basically it's two equations, two unknowns, right? And then two equations, two unknowns, they would actually allow us to find the angular velocity and then the velocity of point B. So if I write VA is equal to VB, right? Plus omega AB cross RA as viewed from B. So this is two equations and then two unknowns. The unknowns here are two equations, two unknowns, which are what? VB, and omega AB, right?
Yeah.
And it is two equations because it is one equation in I and then J direction. So what is VA? VA is equal to minus 4J is equal to VB. I don't know VB, but I know it's going to be in the I direction. Omega AB is going to be downward, right? But still, I don't even need to guess it because when I solve it, I'm going to be able to get it. So minus omega
K.
Exactly, K cross RAB. So what is RAB? They gave us that this guy is 4, 3, and then 5, right? So 3, 4, and then 5. We know this guy is going to make a 90-degree angle, right?
Yes.
So if this guy is 4, 3, and 5, what is the x component of this guy, right? What is the component of AB? Well, we know the total length of AB is equal to how much? 250 plus 300. So the total length of AB is going to be equal to 550 millimeter. Right, okay, so one thing we can do is obviously you can use similar triangles, right? Or you can get this angle alpha, right? Okay.
So it's 550 times 4 over 5.
Yes. Yes, or what I usually like to do is I like to yeah, we can use the similar triangles, and then if I use the similar triangles, I can say 4 4 over this length that I want, right, is going to be equal to 5 over 550, right? Or I can get the angle alpha, right? So 550 times cosine alpha. Okay, the I component طبعا is 550 times cosine alpha, and
Yes.
cosine alpha is equal to 5 over 4. Is that what you said, right? Or no, 4 over 5?
I said 4 over 5. But
Yeah, I think it will be 5 over 4, right?
yes. I think 4
Yeah,
over 5.
4 over 5, yes. And the reason, okay, so let's just, I like to do it simply, like, in baby steps. So what we can do is I can use, okay, so if I use similar triangles, right, I can say that that distance, right? So if every time, if we have this angle, right, I can, we can just like, get the angle. So tangent alpha is equal to 3 over 4, right?
Yes. Yes.
So alpha is equal to inverse tangent of 3 over 4, right?
Which is 36.87.
36.87 degrees, right? And then we have the alpha, then we can just say, this guy times cosine alpha. Okay, I think this would be, like the more an approach that could be used anywhere, right?
Yes.
So this is in the I direction, and in the J direction is going to be minus, right? So minus 550 sine J. And so rewriting that, so minus 4J is equal to VBI. So K cross I again, so we do IJK, and then write one more time, IJK. So K cross I is going to be equal to J, right? So minus omega AB, K cross I is J, so 550 right? K cross I is equal to J. All right, and the next step is K cross J. Coming backward, it's gonna be minus I, but here we have minus, so it's gonna be plus omega AB, right? Times 550. And that is gonna be I, right?
Yes.
Okay, very good. So how many we have two equations, two unknowns, and then we can actually solve for them, right? So I can put the J components together or the I components together, right? So I can basically make this guy equal to 0. I VB plus omega AB, 550 times sine 36.87 will be equal to
It's 330.
330.
Yeah.
Okay, and then the J is going to be equal to, I'm going to move 4 minus I believe that should be equal to, so 550 times 470, that should be 371, right? I think. 371.5. Minus. I'm sorry?
440. If we do 550 times cosine 36.87.
How much did you get? 470, you said?
440.
Okay, 440. Oh my God. Okay, because I just used Google. I think that is why I didn't. Okay. Okay, so here we can first solve for omega AB, right? And then we can use, so we can use this equation to solve omega AB, and then we can use this guy to solve for VB, right? So omega AB, بس هون عندنا issue, so this should be 0.4 ما هيك لأنه this was in millimeters.
Yes.
Right, and then this guy, this 4 is 4 meters per second, right? So omega AB is going to be equal to 4 divided by 0.44 radian per second. And here, this guy is 0, so the J component has to be equal to 0, and the I components have to be equal to 0. So if you divide 4 divided by 0.44, right, it's going to be equal to 9.09 radian per second. So we found omega AB, and from here we can find VB. VB is going to be equal to minus 9.09 multiplied by 0.330, which I think should be 3 in this case.
Yes, minus 3.
3, right?
Yeah.
Okay, minus 3 meters per second. Okay, is this all clear here, or let me see. Okay, do we have any mistakes going on here? Because VB, right, it should be, if this guy is going downward, then this guy should be positive, right? It should be 3 meters per second in either direction. And then here, it seems like we got it in the wrong direction. So I think we may have made like a little mistake over here. And if I take I, this guy is, so VA is equal to VBI plus omega cross I, right? So here, when I'm doing omega, so K cross J, right? K cross J is
minus.
Yeah, so K cross J is minus. ما هيك هنا I have a minus, so this guy is a minus, right?
Yeah.
So here, this guy right there is a minus. Okay, guys, so again, K cross J, right? So K cross J is a minus, so this guy is going to be positive, and minus times positive is going to be obviously minus. So this guy is minus, and this guy here is going to be minus. All right. So ultimately, this whole thing is 0. Then VB is going to be positive. So positive 3 meters per second. Okay. And omega AB is this correct? Also, is omega AB? Is that actually true here? How about here? So K cross I is positive, right? K
Yes. Yes. It's
cross,
J.
yeah, it is J. K cross I is J, and
We have the minus, so it's negative.
okay. So I think what we did is, yeah. So we assumed omega AB is positive like that, right? So here we assumed this guy is rotating like that, and indeed the answer is positive. That means that our assumption that this link is rotating like this, right, in the opposite k direction is positive. But you could also put this guy k to be positive, right? And if you put k to be positive, then this guy would be positive here. And when you actually solve for everything, then you're going to end up here with a minus, right? Meaning that this link is going to be rotating in the opposite direction. Okay, so these are the velocity, the angular velocity of this link, and then now we would actually like, the question is we need to find the velocity of point E. So how do I find the velocity of point E? I think the first step is we have to find the velocity of point D. How do I find the velocity of point D? I can either use VA or I can use VB. Let's keep going and then continue using VA. So here, what I can say here is that the velocity of D is equal
D
to,
isn't a fixed point.
I'm sorry?
D isn't a fixed point, or no?
No, D is not a fixed point because this guy can slide, right? And then this guy is free. D is a point that belongs to this link.
Okay.
You know, it's a pin, so it definitely has a velocity.
Yes.
So what I will do is I'm going to relate that velocity of this point to point A, right? And here, so VD is equal to VA plus omega AB cross R D as viewed from A, right? And now VD is equal to VA. What was VA? Minus 4J, right? And
Yes.
omega AB, we just solve for it, right? Which is 9. And we know it's going to be in the opposite k direction. So minus 9k or 9.09 k cross RD as viewed from A, right? So we need to know the distance from D to A. And from the example that we have, the distance between them is going to be equal to 300, right? So that distance right there is 300 from here to here. So again, this guy is going to be alpha. So what do we do? So it's going to be in the I direction, it's going to be 300 multiplied by cosine of this angle alpha, which is 36.87. And in the J direction, it's going to be a minus, right? Remember, RDA is a vector from, so D as viewed from A, right? It's going to be this vector.
Yes. Yes.
So this guy is going to be minus,
Minus.
right? Minus 300 cosine, right? And then in the J, it's going to be positive, right? Positive 300 sine 36.87. And then this guy is I, it is positive I, and then it is positive J, right? So I'm going to rewrite that. So minus 4J minus 9.09 K cross this is 0.3, like I'm always, okay, sorry, 0.3. Okay, so that is going to be equal to 4j. So k cross I, again, we can rewrite that one more time, ijk, jk. So k cross I is going to be j, right? K cross I is j, and here we have this minus.
And we have the minus.
Yeah, so exactly. Yeah, so k cross j is going to be minus I. So this would be minus 9.09 multiplied by 0.3 cosine 36.87, and k cross I is going to be j.
Isn't a plus?
Yes, but I just wrote it and then I'm going to do the operation. So I have minus and then minus, it's going to be positive, right? Minus and minus is going to be positive, and k cross I is going to be j. So this guy is positive.
Yes.
Now, next step is I have minus, and this guy is positive, it's minus, k cross j is equal to minus I, right?
Yes.
And this again will be positive, right?
Yes.
And here we did what? So k cross j is equal to minus I, so minus, and then this guy is going to be in the I direction. And here, if we continue from here, so j is going to be equal to minus 4 plus 9.09 times 0.3 times cosine right. So now I can basically rewrite that. So we can try and do this now. Okay, let me just do it on MATLAB very quickly. Okay. Anyway, so once we get that VD, right, we can actually use similar relationships, and we are able to find. So I'm gonna quickly do this for you guys now, and going to end up with minus 4 plus 9.09 times 0.3 times.
It is minus 1.81.
I got minus 1.6 on the J. How much did you get?
Minus 1.81.
Minus 1.0. Okay, that is not a big problem. So I'm just gonna keep it. I just did it on MATLAB, and then I got minus 1.62, and then this is on the J, and then let me do the I. 9.09 times 0.3 times sine D of, and then I get here 1.63.
Yes.
I. Okay, so we got the velocity of point D. So now we actually have the velocity of point D, which is this point, right? And we would like to get the velocity of point E. So what we have to do is we have to relate this velocity of this point to this guy, right? And then we can actually solve for omega CE and the velocity of point C. And once we have the angular velocity of this guy, then we can easily use the velocity of point C or D to actually get the velocity of point E. Okay, let us do that, and then we would be done with this. So to do this, basically, I'm going to say that VD is equal to VC plus omega CE cross R D with respect to C. And the velocity of point D is given to me, minus or plus 1.63 I minus 1.62 J is equal to the velocity of point C, which is VCI, right, plus omega CE cross RD as viewed from C. So we need to know these angles, and then this angle is 30 degree, right? So it will be 0.4 cosine 30 I plus 0.4 sine 30 J, and that is this angle here is 30. All right. So from here we can actually solve VC and omega CE, and let's quickly do it. 1.63 I minus 1.62 J is equal to VCI. So omega CE, let's assume it is in a positive K direction, plus omega CE K cross 0.4 cosine 30 I plus omega CEK cross 0.4 sine 30 J. 1.63 I minus 1.62 J is equal to VCI, K cross I, IJK, IJK, K cross I.
J.
Yeah, omega CE times 0.4 cosine 30 J. K cross J is minus I minus omega CE times 0.4 times sine 30. K cross J we said was equal to minus I. Okay, so this is all good. So putting I's together, so I VC minus 1.63 minus omega CE times 0.4 times sine 30 minus 1. So we're done with that, this, and that, plus J multiplied by 1.62 plus omega CE is equal to 0, right? So each one of those is going to be equal to 0. So the first thing that we can do, we can solve for omega CE, right?
Yes.
Omega CE is going to be equal to minus 1.62 divided by 0.4 cosine 30 and 1.62.
It gives me minus 3.5.
Let me just do it with you. 0.4 cos D 30. How much you got?
Minus 3.5.
Exactly, minus 3.5 radian per second. And then that means that the link is going to be rotating in its opposite direction, right?
So in the positive K?
Yes, exactly, right? So if this guy is coming downward, right? Now we assume that CE is in the positive K, right? But in reality, as this guy goes down, this guy is going to be rotating in the opposite K, right? Which makes sense.
Yes.
Right? So if this guy is coming downward, right, this guy is going to be rotating like this, right? As a result of the velocities that we have. So here we said, by the way, the velocity of d is going to be equal to 1.63 and then minus j, minus 1.6. So this point is like somewhere going along this direction. My KVD is going in that direction, and then netlink is rotating like that, and that is why basically we solved omega c to be equal to minus 3.5 radian per second. Now, if I want to find the velocity of point E, I'll simply say V is equal to Vc, right, plus omega CE cross R E as viewed from C. So VE is equal to, do we actually know VC or no?
We can solve it.
Exactly, we can solve it, or we can use VD. How about we use, because we know VD, right?
Yes.
And here RE with respect to D. So V is equal to VD, which is equal to minus 1.62 J plus 1.63 I plus omega CE, which is minus 3.5 K cross RE with respect to D, right? And RE with respect to D is given directly in our thing, which is 0.3 cosine 30 I plus 0.3 sine 30J. And I think that's it, right? This is going to be the velocity of E.
Yes.
Okay. And I want to let you guys, I'm going to keep this as an exercise. You know, done a lot of stuff. I think, you guys should be able to take it from here, do just K cross I, K cross J, and then you can find ultimately the magnitude of this vector V. Okay, because I think now the electricity will be off. Okay, thank you for attending, and the exam is going to be on Friday. Obviously, if you have questions, just reach out to me, and then I'll be more than happy to help you.
Doctor, we will have a long calculation because one calculation mistake with the sign or something will
No,
lead.
of course not. أكيد لا. It's going to be very, very simple, just like what we did in the first exam. We're going to have several multiple questions problems, and then I'm sorry, we'll have some true or false problems, and then I'm going to add just basic problems, like this, not like this obviously, but like the previous exam.
Okay.
And simple solutions, very basic stuff, and I think everyone should be able to do really well.
Yes, because a simple calculation mistake will lead to.
Yeah, definitely. I totally understand that. Yes, definitely. Okay. All right, Lara, take care, and okay, good luck.
Thank you.
Okay. All right. Bye-bye.
Bye.
Bye.